In this lecture, we're going to learn about the properties of light, electromagnetic radiation, that is our principal way of interacting with astronomical objects. Very often in astronomy, we can't touch, we can only see what an object looks like from a distance, and the agency by which we see is electromagnetic radiation. The main question we're going to be addressing in this lecture is, what is light? There are three basic answers that we're going to explore. The first is that visible light is just one of many forms of a larger phenomenon known as electromagnetic radiation. The second is that light can be thought of as a wave or as a stream of particles called photons. And finally, light forms a spectrum from short to long wavelength or from low to high photon energy. And it is these spectra that are going to give us a great deal of information about the physics of the light source, how the light emerges from the source, and how that light interacts with matter between us and the light source as it travels across the universe. The universe contains electrically charged particles, primarily protons and electrons. A charged particle at rest is surrounded by an electric field that stretches out in all directions radially away from the particle, much in the way that the fur on this staticky cat is stretching out in all directions away from the cat. A charged particle in motion, however, is surrounded by a magnetic field. Charges in motion produce electrical currents. Flow of electrical charge and electrical currents generate magnetic fields. Fluctuation in these electric and magnetic fields results in the creation of electromagnetic waves. Here's a computer animation of an idealized electromagnetic wave. The blue arrows represent the strength of the electric field, with the arrowhead pointing in the direction of the electric field, and the yellow arrows represent the strength of the magnetic field, with the arrow pointing in the direction of the magnetic field strength. The first thing you will notice is that the electric and magnetic fields are at exact right angles to each other. The other is that as a changing electric field produces a changing magnetic field, which in turn a changing magnetic field generates a changing electric field. And so the wave is in effect waving upon itself. This is an interesting advance in the understanding of light. People thought of light as waves, and there were lots of experiments in the 19th century that showed the wave nature of light, but there were a great number of arguments over what was the medium it was waving in. When we think of waves, we always think of motion in a medium, water waves or sound waves in air or material waves bounding through a table. But what is light waving on? People made up a substance called the luminiferous ether that filled the entire universe. But it was James Clerk Maxwell, great physicist of the 19th century, who realized that light was, in effect, waving upon itself. A changing electric field leading to a changing magnetic field, which led to a changing electric field, and so on ad infinitum. Visible light is understood to be an electromagnetic wave. However, light is not the only form of electromagnetic radiation. Radio waves are electromagnetic waves, as are microwaves, infrared light, ultraviolet light, X-rays, and gamma rays. This photograph here shows Heinrich Hertz's experimental apparatus for producing electromagnetic waves in 1886. He had a very large static discharge going off here between these two gaps, and then had a receiver which was able to pick up that static discharge and show that it twitched a needle or made a sound in a microphone at some distance. Not too surprisingly, you're making an electromagnetic wave and you're transmitting energy, which is then transmitted into making an electric current in this other device. What Hertz had basically created was a very primitive form of radio. Now, we're going to hear the term Hertz used a lot. The unit of wave frequency for electromagnetic radiation is named the Hertz in honor of Hertz's pioneering experiments in the late 19th century. Waves are a familiar phenomenon. For example, ocean waves. Ocean waves are traveling fluctuations in the height of water. In this case, we have a hump of water and a trough of water moving along, as shown in the little animation there on the left. The other experience of waves in everyday world is sound waves. These are traveling fluctuations in the air pressure. These fluctuations in air pressure, little transverse waves as they're called, wiggles a membrane in the inner ear. Connected to that membrane is a series of bones, which are the bones of the middle ear, which are connected up to the nerve endings. And it's by turning these fluctuations in air pressure into motions of this little membrane, eventually into electrical pulses in the nerves, that allows the human beings, and in fact any animal with a similar ear design, to hear sound waves. Similarly, electromagnetic waves, or light, is a traveling fluctuation. In this case, as we've seen, it is a traveling fluctuation in electric and magnetic fields. The eye is a receiver of electromagnetic waves. Electromagnetic waves entered are focused by the lens in the eye onto the back of the eye, where the cells, which are sensitive to the electromagnetic waves, these waves hitting the cells create chemical changes, which are turned into electrical impulses transmitted to the optic nerve, allowing us to sense light. All of these share a number of basic properties. All can be described in terms of a simple wave. I've drawn the wave here as a computer sinusoid. The wave can be described by a number of numbers. The first of these is the wave amplitude. It's the height of a crest above a trough in a wave. The distance between in a wave, crest to crest, is called the wavelength, and it's traditionally given the Greek letter lambda, which is the Greek L, and therefore stand in for length. Finally, another property of a wave, which is very important to us, is the frequency, which I'm going to denote with the Roman letter F. This is the number of wave crests that are passing a fixed position per second. If this wave were propagating off to the right, and I would see 1 crest, 2 crests, 3 crests, 4 crests per second, that would be a wave with a frequency of 4 crests per second, 4 waves per second. The speed of a wave, v, is equal to its wavelength times its frequency. This is what's often referred to as the wave equation. It says that the wave speed is equal to the wavelength times the frequency. From a pure unit sense, this makes sense. Lambda has units of length. Frequency has a unit of waves per second. So it's length per wave times waves per second. The waves cancel, and I'm left with units of length per time, length per second, which of course is a speed. This is a generic equation for all waves, sound waves, water waves, and even light waves. When we're talking about electromagnetic waves, it's traditional to replace the v in this equation with the speed of light, c. C is a physical constant, and turns out, as we're going to learn through this class, one of the most important physical constants in the universe. And it is exactly defined in the metric system as 299,792.458 kilometers per second. The speed is also independent of the wavelength or the frequency of the electromagnetic wave. Why is it called c? It's called c from the Latin celeritas, meaning fast, and it's in recognition of the fact that the speed of light is the fastest thing in the universe. Let's make a little table comparing the wavelength, frequencies, and speeds of ocean waves, sound waves, and light waves. Typical wavelength of an ocean wave is about 100 meters. That's relatively calm ocean. The frequency at which those waves pass is about 1/10 of a wave per second. It takes about 10 seconds for one wave to pass trough to trough. Therefore, the speed is 100 meters times 1/10 of a second. A typical open ocean wave speed is approximately 10 meters per second. So wavelength times frequency equals speed, and this accords with our observation of how fast water waves might pass by in the open ocean. Sound waves, well, let's take a note like middle C. Middle C has a wavelength of about 1.3 meters. The frequency is 266 waves per second. If you multiply 1.3 meters by 262 waves per second, you get a sound speed of 340 meters per second, a little over a third of a kilometer per second. We should all know approximately what the speed of sound is in the metric system. If you've ever listened to a thunderstorm, a lot of us grew up counting the time between a lightning stroke and when we heard the first roll of thunder. If you do it in metric, what you would find is that if you count 1, 2, 3, boom, after a lightning flash, then you know that that lightning hit approximately 3 times 340 meters, or approximately a kilometer away. So the distance between lightning strikes can be listened by the difference of time of 1 kilometer for every 3 seconds of delay between the lightning flash and when you first hear the crack of the thunder. Keep that in mind for the next thunderstorm. Finally, let's consider a light with a red wavelength. I might be considering a deep red light with a wavelength of about 6.6 times 10 to the minus 7 meters, approximately 0.66 microns, 0.66 millionths of a meter. The wavelengths of light are really tiny. The frequency of light is extremely high, 4.5 times 10 to the 14 waves per second, or put into human words, about 450 trillion waves per second from a wavelength of red light. If I multiply 6.6 times 10 to the minus 7 meters by 4.5 times 10 to the 14 waves per second, I get 3 times 10 to the 8 meters per second. There are 1,000 meters per kilometer, and I get, in round numbers, 300,000 kilometers per second, which is, I've used round numbers here, the speed of light, although you could have computed it with the more exact number that I gave. Typically in this class, when we're doing order of magnitude estimates, we're going to use a round number speed of light of 300,000 kilometers per second. So you can see here the wave equation made manifest. Ocean waves are relatively slow. They have long wavelengths and slow frequencies. Sound waves move faster, about 340 meters a second. They tend to have long wavelengths but fairly high frequencies. And light, which moves at 300,000 kilometers a second, will have a combination of, for visible light, very short wavelengths and very high frequencies. Of course, different types of light will have different combinations of these numbers. The other property of light that interests us is that light carries energy. For example, sunlight. You can see sunlight here carrying energy. The plants absorb the sunlight, use that energy to cause chemical reactions to occur that build up sugars, convert carbon dioxide into oxygen through photosynthesis, and eventually those sugars, combined with nutrients and water taken up from the soil, can be stored into an apple. You could then take some of that chemical energy. When you eat the apple, it goes into your body. In a sense, when you're eating an apple or a piece of fruit, you are actually eating sunlight, which has been stored in an indirect way in terms of chemical energy. That sunlight is energy being brought from the sun by electromagnetic radiation, by visible light. In the end, the sun is powered by nuclear fusion, and so the energy we get from eating an apple had its ultimate source in nuclear fusion in the center of the sun. A more everyday example of the use of light as a source of energy is shown in this industrial laser cutter. The laser beam is cutting through this piece of metal, making a very high precision circle inside of it. Industrial lasers and other things are good examples of how light and its energy can be concentrated and put to use. Light also carries information. For example, information can be encoded in a light wave by modulating its amplitude, how much it goes up and down. And indeed, radio waves, in which we encode sound information by modulating the amplitude up and down, is the basis of AM, or amplitude modulation radio. If instead we keep the amplitude more or less constant, but vary the frequency back and forth, and encode information, so different sounds and frequency, different sounds are encoded here, we have frequency modulation, or FM radio. Light can be described as a wave, and a lot of information can be gained about electromagnetic radiation from the wave picture. But as we're going to see in the next part of this lecture, that's not the only way, and only useful way, that we can describe light.